I'm Kazuki Shibanuma from the University of Tokyo, Japan. Today, I will talk about a microscopic model for simulating grain boundary diffusion creep in polycrystalline solids. This slide shows the table of contents of this presentation. I will show you the research background first. So, the performance of combustion devices such as power plants, turbines can be improved under higher temperature and stress conditions. It is a basis for driving various technological innovations. So, for this purpose, a key technology is controlling high temperature creep damage. However, the actual service time of these components is for even several decades. So a priori testing under actual operating condition is actually impossible. To develop high performance material and to optimize operation and the maintenance of components, if we have an accurate prediction model for creep life, it must be significantly effective. However, such models have not been established yet. This is because a creep phenomena is derived from nano and micro scale mechanisms such as vacancy diffusion, or diffusion growth, and grain boundary migration, and result in macro scale responses such as deformation and failure. This quantitative relationship has not been clarified yet. So the creep phenomena is governed by Maltz scale and Maltz physics, which is extremely complicated. In this study, to quantitatively explain the macroscopic response based on the nano and microscopic scale mechanism, we employed two kinds of operating strategies. First, we focused on interconnection between factors from each discipline, such as mechanics of materials, metallurgy, and crystallography, and thermodynamics. And second, we focused on grain boundary diffusion, copper creep alone, which is most critical mechanism for actual long-term operation for simplification. Then I will show you the model development numerical example. And this slide shows the outline of the developed model. We developed a model by integrating three sub-models: microstructure, deformation, and void unification growth. So it's a comprehensive modeling approach of peak deformation and damage in polycrystalline solid. I will show you respective sub-models in following slide. This slide shows a microstructure model and calculation flow. We developed a model as a representative variable element RV model like this, and we generate polycrystalline structure using open source software neighbor concerning the periodic condition. And this part, and right hand side is the calculation flow of the model. After generating the polycrystalline structure, we repeated two kinds of simulations, deformation and void unification rules, respectively. This slide doesn't work well, but I will explain the outline of the deformation model. The copper creep deformation can be assumed as the superposition of two kinds of grain growth mechanism, the grain boundary migration and the grain boundary diffusion. For grain boundary migration, its driving force is the reduction of the total grain boundary energy. So, based on the principle of minimum potential energy, we evaluate the velocity of the quadruple points using this simple calculation unit. For grain boundary diffusion, first, from the normal stress on each grain boundary facet, we evaluate chemical potential of each grain boundary facet. And then from the difference of the chemical potential between adjacent grain boundary facets, we evaluate diffusion flux across the turbulent lines. And then as a summation of the diffusion flux, we can evaluate relative grain boundary velocity, which is a key parameter to describe this phenomenon. Microscopic strain rate tensor and velocity of the corridor point can be evaluated based on this relative grain boundary velocity. And geometry of the polycrystalline structure is updated based on the velocity of the corridor points from these two models. And this slide shows the outline of the void nucleation Bruce model. In this model, we employed two assumptions for simplification. The first one is the void shape. We assume the void shape as a portion of a rotational ellipsoid, like this. And second one is the calculation unit. We assume that each grain boundary facet as an independent calculation unit for simplification. For void nucleation, its nucleation rate is quantified as a function of relative grain boundary velocity based on experimental results. And its initial size is determining the stability condition for void existence. And void growth is evaluated based on this governing equation expressed as Poisson's equation. And by solving the normal stress distribution to satisfy the condition of void boundary triple lines and the equilibrium applied stress, we obtain the normal stress distribution on each grain boundary facet. Based on this stress distribution, we can evaluate the change in void volume and void shape based on the diffusion flux around the void and that on the void surface respectively. And this slide shows a numerical example of developed model. We can see the void nucleation growth behavior in this polycrystalline structure like this. And of course, we evaluate the normal stress distribution on each grain boundary facet, so we can visualize it like this. And because of the probabilistic nature of the developed model, we can see realistic scatter in evaluation of the void area fraction in each grain boundary facet. So I will move to the model validation compared with theoretical formula and experiments. First part is a validation for the deformation. So for copper creep, we know some theoretical formula of the strain rate as described this expression. So there are several factors to determine the strain rate. I will show you two of them as a typical example. The first one is applied stress effect. So we performed systematic simulations with various applied stress conditions. Then we got these results. As we can see, minimum strain rate requires completely proportional to the applied stress. That is, which is perfectly coincident with theoretical formula. And the second example is the effect of the grain size, average grain size. So similarly, we performed the systematic simulations with RBEs having various average grain size, and we got these results. As we can see, the minimum strain rate was proportional to the inverse of cube of average grain size, which is also perfectly coincident with theoretical formula. That is a validation for the deformation model. And then I will show you the validation of the void nucleation growth. So unfortunately, we don't have any appropriate theoretical formula for void nucleation growth behavior. So we compared with experimental results. After uniaxial grip test using pure nickel, we machine sample for void formation observation for void formation like this. And we quantify the void fraction in cross-section as a cumulative function of grain boundary angle based on this kind of image analysis. And then we got a characteristic curve like this, which is a relationship between grain boundary angle and void fraction. And we performed completely same procedure in numerical results like this, and then obtained this. And so this is a compared results. So we can see very good agreement between them. So we found that the developed model can accurately reproduce the clip void formation in a 3D polycrystalline structure. Then I will show you some application example for design. The first example is application to the external loading design. So we investigated the effect of the stress triaxiality. As everyone knows, the experiment under triaxial condition is not easy. But of course, using this model, we can investigate the effect of any kinds of arbitrary loading condition very easily. So we investigated the effect of the stress triaxiality. As a result, we can see the deformation can be quantified based on equivalent stress, which is coincident with conventional knowledge. And also, higher stress triaxiality. So we know higher stress triaxiality accelerates the void nucleation Bruce behavior. We could quantitatively evaluate such tendencies. And the second example is application of the material design. So we investigate the effect of the grain size distribution. Although the effect of the grain size is very well known, but the effect of other microstructure factors are largely unexplored. So we investigate the effect of the grain size distribution using the RVEs with equivalent average grain size but different distribution like this. So as a result, we found that greater variance leads degradation of the performance in any case. So these results demonstrate the potential of the developed model as a design tool. So maybe time is over. Sorry, I will skip the summary part. And I want to introduce only this slide. So it's a possible collaboration and code sharing. So if you are interested in our work, I'm very happy to discuss collaborative opportunity. So our Python source code of our RV model can be shared upon your request. So please feel free to contact me. That was my presentation. Thank you very much.